Have you ever felt like you're trying to solve a puzzle, maybe in business, maybe somewhere else, with just too many pieces and, well, not enough space on the board?
Happens all the time.
Exactly. Whether it's running a company, planning a project, even just sorting your day, we're always up against limited resources, time, money, people, materials.
And tons of choices on how to use them.
Right. And the big challenge is always, how do you make the best call, the decision that gets you the most of what you want? Maybe profit, maybe efficiency when everything feels tight. Today, we're really going to dive into a powerful tool that helps with exactly this. It's called linear programming. We'll explore how it guides businesses especially to make optimal choices when they face these kinds of limitations. And we've got a specific example lined up to make it all feel, less abstract and more real.
Yeah, and our mission here really isn't just to walk through the calculations, though we'll touch on that. It's more about uncovering the strategic insights it gives you for management decisions, particularly how it helps when things change, like resource availability. Understanding that can really shift how a company thinks about, well, everything, growth, profit.
Okay, let's jump into this example then. So picture a company, their main goal, maximize profit. Standard stuff.
Standard, yeah.
They make two products. Let's keep it simple. Product X and product Y. But like any real business, they've got limits, hard limits.
The constraints.
Exactly. They have a maximum of 16,000 hours of labor available and their material supply, capped at 15,000 kilograms. That's all they get.
Okay, clear limits.
Now, for the products themselves, to make 1 unit of product X, they need 3 kilograms of material and 4 hours of labor. And that unit brings in $30 of contribution to profit.
Got it. 3 kilos, 4 hours, $30.
Then there's product Y. It uses more material, 5 kilograms, but the same amount of labor, 4 hours, but it contributes more, $40 per unit.
Ah. Okay, so there's the trade-off right there. Y gives more profit per unit, but eats up more of that limited material.
Precisely. You can already feel the tension, can't you? Making more of Y might seem good for profit per unit, but you'll run out of materials faster.
Right. And this is where linear programming starts to structure the problem. The first step is defining your variables. Simple enough here. X is the number of units of product X we make, and Y is the number of units of product Y.
Makes sense. X and Y.
And you build what's called the objective function. It's just a mathematical way of saying what you're trying to achieve. Here, it's maximizing the total contribution.
Which is profit, basically.
Essentially, yes.
Yeah.
So the function is C equals 30 times X, the contribution from all units of X, plus 40 times Y, the contribution from all units of Y. So C equals 30X plus 40Y. Our goal is to make C as big as possible.
Okay, maximize C equals 30X plus 40Y. Got it. And then we bring in those limits, the constraints.
Exactly. They become inequalities.
So for materials, it takes 3 kilos for each X and 5 kilos for each Y. And the total can't be more than 15,000 kilos.
So 3X plus 5Y must be less than or equal to 15,000. That's our material constraint.
3X plus 5Y, 15,000, and labor. It's 4 hours for X, 4 hours for Y, and the total can't exceed 16,000 hours.
Right. So 4X plus 4Y is less than or equal to 16,000.
4X plus 4Y, 16,000. And obviously you can't make negative products, right?
Huh. Good point. Crucial, actually. So X has to be greater than or equal to 0, and Y also has to be greater than or equal to 0, the non-negativity constraints.
Okay. Now, I remember doing this graphically back in the day. You can actually plot these inequalities on a graph, can't you?
You absolutely can. Think of a graph with X on the horizontal axis and Y on the vertical. Each of those inequalities defines a region. The lines themselves are the boundaries.
Right. So for the materials constraint, 3X plus 5Y equals 15,000. That line would connect the point where X is 0. So Y would be 3,000.
Exactly. The point.
It says 3,000.
And the point where Y is 0. So X would be 5,000. The point, 5,000, 0.
Correct. Connect those 2 points, and everything below that line, and including the line, satisfies the material constraint.
And same for labor. 4X plus 4Y equals 16,000. If X is 0, Y is 4,000. If Y is 0, X is 4,000. So that line connects 0, 4,000, 4,000, 0. And again, everything on or below that line is okay for labor.
Plus, we can't go below 0 on either axis.
Right. So when you put all these constraints together, materials, labor, and non-negativity, they fence off an area on the graph, usually a polygon.
And that's the feasible region.
That's it, precisely. The feasible region. It represents every single possible production plan, every combination of X and Y that the company can actually produce without breaking its own rules. without exceeding its resource limits.
So any point inside that shape is a possible production plan?
Any point inside or on the boundary, yes. And the magic, or rather the method of linear programming, is to find the point within that feasible region that gives the highest value for our objective function, c equals 30x plus 40y.
How do you find that specific point?
Well, graphically, you can imagine that objective function, c equals 30x plus 40y, as a line too. You can plot it for a certain level of profit, say $100,000. Then you imagine pushing that line outwards, keeping its slope the same as far as you can without leaving the feasible region.
Okay. Pushing it out until it just touches the furthest corner point of that feasible shape.
Exactly. The optimal solution in these kinds of problems almost always occurs at one of the corner points or vertices of the feasible region.
And in our example, where does it land?
It lands at point B, which is the intersection of the materials constraint line and the labor constraint line.
So the spot where both resources are being fully used, that makes intuitive sense. That's where things are tightest, maybe?
It often works out that way when both resources are limiting. It's the point where you're using exactly 15,000 kilograms of materials and fee exactly 16,000 hours of labor.
Okay, the aha moment. So what is that point? What's the actual production plan?
Well, you solve those two equations simultaneously. 3x plus 5y equals 15,000 and 4x plus 4y equals 16,000. And when you do the math...
Don't make me do the math live.
No, I've got it here. The optimal solution is x equals 2,500 units.
Okay.
And y equals 1,500 units.
So 2,500 of product X and 1,500 of product Y. That's the sweet spot.
That's the sweet spot. And if you plug those numbers back into our objective function, c equals 30x plus 40y, you get 30 times 2,500 plus 40 times 1,500.
Which is $75,000 plus $60,000, $135,000.
Bang on. $135,000. That's the maximum possible contribution the firm can achieve with its current resources and products. It gives management a really clear target.
That's powerful. It takes the guesswork out, but the real world isn't static. Things change.
Always.
What if, say, a supplier calls up and says, hey, I've got some extra material I can sell you. Now things get interesting. How much should the firm be willing to pay for that extra material? And maybe just as vital, how much should they even buy?
Excellent questions. And this is where we move beyond just finding the current optimum and into understanding the dynamics. This brings in the concept of the shadow price.
Shadow price. Okay, I've heard that term. What does it mean in this context?
So for each constraint in our case, materials and labor, there's a shadow price. It tells you how much your objective function, your total contribution C, would increase if you could get just one more unit of that constrained resource.
One more kilogram of material or one more hour of labor.
Precisely. And for our example, the calculations show that the shadow price for materials is $5 per kilogram.
Okay, $5 per kilogram. So what does that tell the manager?
It tells them that if they could get one extra kilogram of material, their maximum potential profit would go up by $5, assuming, crucially, that the current constraints remain the binding ones.
Right. So if their normal cost for materials is, say, $8 per kilogram.
Which we didn't explicitly state before, but let's assume it's 8 kilograms, yeah.
Then this shadow price of $5 means they should be willing to pay up to an additional $5 over their normal cost for extra material.
Exactly. They should be willing to pay up to $8 plus $5, so $13 per kilogram total for any extra material offered.
Because up to that price, acquiring more material still increases their overall profit.
Yes. If they can get it for, say, $12 per kilogram, they're paying $4 over their normal price, but that kilogram allows them to generate an extra $5 in contribution. So they're still $1 better off overall for each kilogram they buy at that price.
Okay, that makes sense. It quantifies the value of loosening that specific constraint.
It puts a hard number on how much that bottleneck is costing you, or rather, how much it's worth to ease it.
But here's where, the real world gets messy, doesn't it? The calculation says don't paying more than $13. But what if paying $14 per kilogram lets you satisfy a really important customer order?
Right. Or maybe avoid a huge penalty clause in a contract.
Yeah. Those factors aren't in the basic linear programming model, are they?
Not typically.
Yeah.
The shadow price gives you the direct financial impact on contribution based only on the model's variables. Strategic considerations, customer relationships, long-term contracts, market reputation, avoiding penalties. Those are qualitative factors management has to layer on top.
So a manager might rationally decide to pay more than the shadow price suggests for strategic reasons.
Absolutely. It happens. The model provides a crucial piece of financial information, but it's not the whole decision.
And what about the flip side? What if they get offered material really cheap, say way under $13? Is it always a no-brainer to buy it?
Not necessarily. This is where other factors come in again.
Right.
What about the quality of that cheap material? Is it up to standard?
Good point. Or the supplier, are they reliable? Will they deliver on time? If you rejig your whole production plan based on getting more material, and then it doesn't show up.
Exactly. You could be worse off. So the takeaway here, especially maybe for accountants or finance folks looking purely at the numbers, is that price isn't everything. The shadow price is incredibly useful. It tells you the financial wiggle room, but you have to consider quality, reliability, strategic fit, the whole picture.
That's a really crucial point. The model is a tool, not the entire strategy. Okay, so let's say they do decide the price is right, the quality is good, the supplier is solid. How much extra material should they actually buy? Is there a limit?
Oh, definitely there's a limit. Think back to that graph.
Okay, the feasible region.
As you get more materials, that material constraint line, 3x plus 5y equals 15,000, starts to move outwards, away from the origin. Your feasible region gets bigger.
Which means you can potentially make more profit.
Correct. But it only moves outwards so far before something else stops you. In our case, the labor constraint, 4x plus 4y equals 16,000, is still there.
Okay. So eventually the material line moves so far out that it's no longer the thing holding you back. Labor becomes the main bottleneck.
Precisely. There's a point where having even more material wouldn't help at all because you simply wouldn't have the labor hours to use it effectively, according to the optimal plan shifts.
So how do we find that limit? Where does buying more material stop making sense?
You look at where the relaxing material constraint would eventually mean that only the labor constraint is truly binding. If labor was the only constraint, remember the line was 4x plus 4y equals 16,000. And given the higher contribution from y, 40 versus $30, if you only had a labor constraint, you'd want to make as much y as possible.
Which would be, if x is 0, y is 4,000 units, 0.04,000.
Exactly. So the theoretical maximum production, if materials were no object at all, would shift towards making only product y up to the labor limit of 4,000 units.
Okay. And how much material would you need to make those 4,000 units of y? Product y uses 5 kilograms each.
So 4,000 units times 5 kilograms per unit. That's 20,000 kilograms.
20,000 kilos. But they only have 15,000 kilos right now.
Correct. So the maximum amount of extra material that would be beneficial for them to acquire is the difference. 20,000 kilos needed at that theoretical labor-only limit point, minus the 15,000 kilos they currently have.
Which is 5,000 kilograms.
That's the limit. Beyond acquiring an extra 5,000 kilograms, any further material just sits there because they'll be completely maxed out on labor trying to make mostly product Y. The shadow price of material would effectively drop to zero at that point because more material offers no additional profit. Labor's shadow price would then become the significant one.
Wow. Okay. So the model not only tells you the value of getting more resource, the shadow price, but also the quantity beyond which it stops being valuable.
Exactly. It helps you understand the interplay between your constraints.
This has been quite a journey. We started with a firm, 2 products, clear limits.
Define the variables, the objective, the constraints.
Found that optimal production plan 2500X, 1500Y for 135K profit.
Yep.
And then really unpacked what happens when things change, that shadow price concept. $5 for materials telling you what extra resources are worth.
But also the limits to that, both the qualitative factors like customer needs and quality.
Right. Price isn't everything.
And the quantitative limit only needing up to 5,000 extra kilos before labor takes over as the bottleneck.
It really shows how these, seemingly complex mathematical models can give really clear, actionable insights for managers.
They absolutely can. They provide a strong foundation, a starting point based on optimizing the numbers. But as we discussed, effective decision-making always needs that layer of real-world context, quality, reliability, strategy, relationships. The math points the way, but human judgment steers the ship.
So thinking about this, maybe for everyone listening, what does this mean for you? Think about some constraint you face, maybe at work, maybe personally, a tight budget, limited time, maybe even just energy levels.
Yeah.
Could framing it mathematically, even just roughly, help you see an optimal point you hadn't considered? Or reveal a kind of shadow price? How valuable would just a little bit more of that constrained resource really be to you?
It's a fascinating way to think about trade-offs.
It is. And it makes you wonder how often we focus too much on just one limitation when the real key is understanding how all our resources connect and interact. That's where the maximum value often lies, isn't it? Finding that balance.